All right, guys, today we're going to be talking about improper integrals. And so we want to ask and answer the question, what is an improper integral? Well, an improper integral is an integral that meets one of these two conditions, either one or both of the limits of integration are infinite, all right, or the function has an infinite discontinuity somewhere in the limits of integration. So let's say, for sake of argument, we had the integral from, let's say 2 to infinity of the function 1 over x squared dx. Well, we know that 1 over x squared looks like this, but it never actually touches the x-axis. All right, and so let me actually extend that out a little bit. And so you are finding area that really never ends. That's called an unbounded region. An unbounded region. Because technically, if you go from 2 to infinity, it never ends. You're going to get an infinite amount of area, all right? Or another example of an of an improper integral would be, let's say we integrated this same function from -2 to 3 of 1 over x squared. Well, that's a problem because x cannot be equal to 0. If you have x equal to 0, then you're going to be dividing by 0, which means that will be an undefined situation. So there is an infinite discontinuity or a vertical asymptote, which is another example of when you would get an infinite amount of area because the curve goes up forever. So if you come up across an integral that has either one of these two conditions, it is an improper integral, and we need to find a way to integrate it. So in this particular situation, what you do is you pick a point way out here that is a finite point that you're going to integrate to. So let's say this problem, we will integrate from 2 to, let's say, the letter b of 1 over x squared, because we know that if we integrate from x equals 2 to x equals b, that is a finite area. We can find that. And then you turn the problem into a limit problem, and you're going to take the limit as b approaches infinity. And so that is the way that we're going to evaluate the area under the curve, or at least approximate it, all right, by turning it into a limit problem. All right, here we have the improper integral, and we know it's improper because we have one of our limits is infinity, and so we are going to integrate this function from 1 to the letter b, and then we're going to turn this into a limit problem and let the limit as x approaches, not as x, but as b approaches infinity. And you may say, well, why do we have to do this? Because technically you cannot evaluate a limit when it has an infinite limit. So we're going to pick the letter b as a finite number and integrate from 1, which is a finite number, to another finite number b, evaluate the limit, and then evaluate the integral, and then let b go to infinity. All right, so 1 over x dx, and that is going to end up giving us the natural log of x evaluated at b to 1. And so that's going to be the natural log of b minus the natural log of 1. Natural log of 1 is simply 0, so that goes away. And so now we are left with the natural log of b, and we are going to take the limit as b approaches infinity. And so we now recognize that the natural log curve looks like this. And so as the value of b, or the x, goes to infinity, so does the natural log of b. It goes to infinity as well, and so the answer to this would simply be infinity. And anytime you get an integral that goes to infinity, you will say that that integral diverges. Diverges. All right, we're going to do the next problem now. All right, once again, we are going to evaluate the integral from 0 to infinity of e to the negative x dx. And so we will start by once again turning this into a limit problem. So we're going to evaluate from 0 to b, and we're going to let b approach infinity of e to the negative x dx. All right, so we're going to integrate e to the negative x, which is simply negative e to the negative x, evaluated at 0 to b. We're going to plug in our upper limit, and that's going to give us negative e to the negative b, minus plugging in the lower limit, and that's going to give us negative e to the negative 0, which is just 0. So that's going to be negative 1. So that's simply going to be negative e to the negative b plus 1. All right, and maybe it'd be helpful if we wrote it as negative 1 over e to the b, because anytime you have a negative exponent, you can move that to the bottom. And so we have negative 1 over e to the b plus 1. And then we are going to take the limit as b approaches infinity of negative 1 over e to the b plus 1. Well, we can see that as b approaches infinity, e to the b also approaches infinity. So you have negative 1 essentially over infinity, which is going to be approaching 0, plus 1. So this integral would converge. It's going to converge to 0. And that is the answer to this first one. All right, let's take a look at the second one. We have the integral of 1 over x squared plus 1. So once again, we're going to integrate from 0 to, we'll just say c this time. And the limit as c approaches infinity. And 1 over x squared plus 1 dx. All right, if we integrate this, we recognize this to be the inverse tangent of x, evaluated at the upper limit minus the lower limit. And then we plug in our c, so inverse tangent of c minus the inverse tangent of 0. All right, well, the inverse tangent of 0 is simply 0, so that's going to go away. All right, so that's something that you need to make sure you understand why that is 0. I'm assuming that you know that. And then the inverse tangent of, well, you got to plug infinity in for c, so essentially we're looking for the inverse tangent of infinity. Well, if we remember what the inverse tangent graph looks like, it would be helpful to recognize this, that there are asymptotes at pi over 2 and negative pi over 2, and the graph of the inverse tangent kind of looks like that. So as x approaches infinity, the inverse tangent graph approaches pi over 2. So this integral is going to converge to pi over 2. All right, guys, this is an ugly problem. I'm just warning you ahead of time. All right, this is a problem that we're going to have to use integration by parts and L'Hopital's rule with an improper integral. Ugh, man. All right, let's see if we can start by distributing the e to the negative x in here. And once again, so we're going to have the limit as b approaches infinity of 1 to b e to the negative x minus x e to the negative x dx. All right? And so now we are going to break this up into two integrals. And the integral of 1 to b of e to the negative x is simply just negative e to the negative x. All right, so that is the first integral. And then this integral, this part of the integral right here, unfortunately we're going to have to use integration by parts there. So we're going to put a minus, all right, and then we're going to put a bracket, and then we're going to pay attention to simply the x e to the negative x. So we're going to let u equal x, and we're going to let dv equal e to the negative x. So that means du is simply 1 dx, and v is the integral of e to the negative x, which would be negative e to the negative x. All right, so we're going to plug that into our integration by parts. So uv is going to be negative x e to the negative x. So that's going to be uv minus the integral of v, which is negative e to the negative x, du, which is just dx. All right. Now there's a couple things we can do here. This minus and minus, we can just make those pluses to make our life a little easier. And then we can integrate e to the negative x. So that's going to come down, and that is going to be, once again, negative e to the negative x. All right, and so let's see all that we have here. Let's collect up our terms. We're going to bring this guy down, and we have negative e to the negative x. We're going to distribute this negative in here, and that's going to give us plus x e to the negative x. And then we have this guy right here, and that's going to be negative e to the negative x. Excuse me, it's going to be positive because this negative has got to distribute to that negative. It's going to be positive. So we see that that term and that term are going to conveniently cancel, and all we're going to be left with now is the integral from 1 to b, the limit as b approaches infinity of x e to the negative x. All right, so we're going to plug in our upper limit of b. That's going to give us b e to the negative b, and then the lower limit is going to give us 1 e to the negative 1. All right, and then we are going to move this down to the bottom, and so then that's going to end up giving us b over e to the b minus 1 over e to the first, because I'm going to simply move that down as well. And now we're going to let the limit as b approaches infinity. All right, so as b approaches infinity, notice that we get infinity over infinity for that particular term. So that's going to be a L'Hopital's rule problem. So we're going to have to take the derivative of the top, which is 1. We're taking the derivative with respect to b, and then the derivative of e to the b is simply e to the b. And so then we're going to, once again, take the limit as b approaches infinity of this. So you have 1 over infinity, which is simply 0. But we can't forget about that term. Well, let's just think about this. 1 over e is simply a constant, and the limit as b approaches infinity of any constant is simply just going to be that constant. So, after all of that work, the limit in the integral is going to converge to negative 1 over e. Very confusing problem, and expect some questions on this one. All right, here's another tricky one here. We are going to integrate, and notice that both of the limits of integration are infinity or negative infinity. So when you have a situation like this, you need to actually break the integral up into two integrals, and so we're going to do that. So the first integral is going to go from negative infinity, and you can choose where you want to break it up. You could go from negative infinity to 1 and then from 1 to infinity, but I'm going to choose 0 just because oftentimes 0 is pretty easy to plug in. And so I'm going to integrate from negative infinity to 0 and dx plus the integral of 0 to infinity of the same expression. And then we are going to turn this into a limit problem. And so it is going to end up being, we're going to have to let b, so why don't we say the limit as b approaches negative infinity. So this is going to be the integral from b to 0 of e to x, 1 plus e to the 2x dx, plus the limit as we'll say as c approaches infinity of 0 to c e to the x over 1 plus e to the 2x dx. All right? And so now we are actually ready to integrate, so we are going to do a u substitution, and we are going to let u equal e to the x, du is going to equal e to the x dx, and so du over e to the x equals dx. So now we can plug in, and we're going to end up getting 1 over 1 plus u squared, because the e to the x is going to cancel out. All right, so this is going to end up being, all right, the integral from b to 0 of this function, which is going to end up being the inverse tangent of u, but u is e to the x. All right, so at least we know that this integral and that integral are going to end up being the same, so we don't have to do it twice. And so let's just kind of continue over here. So our first integral is going to be the limit as b approaches negative infinity, and we've already integrated, so inverse tangent of e to the x plus, and maybe we'll do this one in white, the limit as c approaches infinity of the same function, inverse tangent of e to the x. All right, now is where the fun comes in. Now we got to plug all these numbers in, and we're going to integrate. So we're integrating from 0 to b, and this one is going to be from 0 to c. All right, so we're going to plug in our 0 into inverse tangent of e to the x. Well, e to the 0 is 1, so we're going to have the inverse tangent of 1, all right, minus the inverse tangent of e to the b. Well, b is going to negative infinity, so e to the negative infinity. All right, so the inverse tangent of 1 is simply 45 degrees, or pi over 4. And this is where it gets a little tricky here. We're going to move this e to the negative infinity to the bottom. So that's going to end up being the inverse tangent of 1 over e to the infinity. Well, what is 1 over e to the infinity? Essentially 0. So inverse tangent of 0 is simply 0. So that's going to be our upper and lower limit of our first integral. And then we are going to plug in our upper lower limit of our second integral. And so we will plug in c into our other inverse tangent. So that's going to end up being inverse tangent of e to the c, but in this limit we're letting c approach infinity, and so e to the infinity, all right, minus inverse tangent of e to the 0 once again, so that's just simply going to be 1, all right, and so the inverse tangent of 1 is pi over 4. And earlier in this video we said that, well, e to the infinity is simply infinity, and if you remember what the inverse tangent graph looks like, it is going to have asymptotes at pi over 2. So as x approaches infinity, the inverse tangent is going to approach pi over 2. So we have pi over 4 that I'm circling plus pi over 2 minus pi over 4. Well, these two are simply going to cancel, and that's going to leave us with an integral that converges to pi over 2. That is the value of this improper integral. All right, last problem here, and now we're going to integrate a function that is discontinuous when x is 0. All right, so we notice here that from the denominator, x cannot be equal to 0. And so that is a problem. So we are going to have to break this integral up into two integrals. The first integral is going to go from -1 to 0, 1 over x cubed dx, plus the integral from 0 to 2 of that same function. But there's a problem. Remember, we just said x cannot be equal to 0. So therefore, we cannot have 0 as one of our upper or lower limits. So we are going to essentially integrate from -1 to some finite number b that is really close to 0 but not quite equal to 0, so that we can get an integral value, and then we're going to let b approach 0 from the left side first and then from the right side. So we're going to rewrite this as the limit as b approaches 0 from the left of -1 to b, 1 over x cubed dx, plus, and this one is going to be the limit as c approaches 0 from the positive side, and this is going to go from c to 2 of the same function. Alright, so now we're going to integrate 1 over x cubed, and we're going to end up getting -1 over 2x squared. And that's going to be evaluated from from -1 to b. And so we are going to plug in our upper limit, which is going to be b. So it's going to be -1 over 2b squared minus, plugging in the lower limit, square -1, you get 1 times 2 on the bottom, so that's just going to give us a -1/2. And that is the upper and lower limit plugged in to the first integral. And then the second integral, we're going to plug in 2. Okay, so actually, let's just remind ourselves that integral is going to be -1 over 2x squared. So we're going to plug in 2, and we're going to get -1/8. All right, so that's going to be -1/8. And then let's plug in the lower limit of c, and that is going to be -1 over 2c squared. All right, and now we are going to let b, so we're going to let b approach 0 from the negative side, and then we're going to let c approach 0 from the positive side. Okay, so looking at this first term right there, well, if b is approaching 0, then what you're going to have is a negative 1 over 0, which we're going to call infinity, negative infinity. So we're going to have negative infinity plus 1/2, because of minus and a minus are going to end up giving us pluses. And then we have a minus 1/8. And then we're going to let c approach 0. So actually, let's make these both pluses right there. And then we're going to do the same thing. We're going to let c approach 0. So you're going to have 1 over 0, which is once again going to be infinity. Now, here's the tricky part. This infinity and that negative infinity are not the exact same value. So you just have to assume that those two infinities added together are going to be some infinite number. All right, and so you're going to end up having infinity plus 1/2. All right, so anytime part of your answer is infinity, then the entire answer is going to be divergent, which means the integral of f of x is undefined. All right, it is undefined. It goes to infinity, so that is the answer to this problem.